Hello everybody, my name's Sarah Hunak and I'm the current chair of the SRP webinar working group, and I'd like to welcome you to another SRP webinar this lunchtime on an introduction to clearance. In terms of number of attendees today, we've had more than 420 people register for this webinar from all over the world, which I think might be some kind of record, which is great. Pete really does know how to draw a crowd. Thank you all for tuning in and supporting us. Next, just a couple of ground rules. Apologies to all the frequent flyers who've heard these before. I'll just spend a couple of minutes on them. So firstly, questions. You can ask questions at any point through the Q&A box. There should be a little icon of a question mark inside a speech bubble on your screen. If you click on that, you'll be able to ask a question at any point during the talk. You can also like any questions published there to upvote them. Then at the end, the most liked ones will be the ones that are put to Pete and he'll answer them for us. Any that we don't get time to answer today will be posted to our events page. In terms of registering your attendance and being able to claim CPD points for your attendance, please email Charlene, her email's up there on the screen, with the code clear%#, and you'll get an email confirmation to show the CPD points that you've claimed today. And then finally, feedback. Please let us know how you think these webinars are working out and if there's anything that we can do to improve them. There'll be an online survey link sent after the webinar for you to fill in. So after this webinar, we've got plenty lined up. We've got a review of radioactive liquids in a couple of weeks' time and activity assessment of radioactive waste, as well as radiological risk assessments coming up in April. Let us know if there are any more topics that you'd like us to cover or if you fancy presenting one yourself. Finally, whilst you're here, if you're not already a member, just like to do a quick plug of the benefits that you could be getting if you were a member. You'd get the Society Journal and a weekly e-newsletter. You can get a discount at any of our conferences and full-day virtual events. And it's just a really good way to keep up to date with the radiation protection community in general, get access to job vacancies and get involved with SRP committees. So if you do fancy joining, then head over to our website after the webinar to sign up. Finally, professional status. We currently offer these 3 levels of professional registration. If you pop over to our YouTube channel, there are some videos describing what they are and how to apply for them. And there is a plan to run a future webinar on this topic too. So without further ado, I would like to introduce our speaker, who probably doesn't need any introduction, to be fair, Pete Burgess. So Pete started his career at NRPB about 30 years ago, delicensing reviews, finding radium dials, sorting through a huge heap of lead and zinc concentrate, which came with free and very unexpected and unwelcome cesium-137, and checking out radiochemistry laboratories. It was interesting. He then moved to UKAEA 19 years ago, where the point of the organisation was to make itself disappear, with the exception of fusion research. And the facilities covered almost every aspect of radiation research. Whilst there, he was appointed as the instrument and measurement geek to the Clearance and Exemption Working Group, which widened the scope to include Sellafield and other parts of the nuclear industry. Life at MPL followed, continuing with the Clearance and Exemption Working Group, and now with projects at Naval Dockyards, then to Nuvia in the same sort of role, and then to Radiation Metrology Limited. Scope has gently widened to include IAEA missions and publications, teaching in Italy on the subject regularly and helping with the emission site, but still making prototypes of strange detectors in the workshop, which sometimes are one-offs, but others of which get developed. So thank you for joining us, Pete. Over to you.
Yeah, greetings. Nothing like quiet introduction. Let's find the right page. No, I've lost it. There it is. Let's go. Right, from the beginning. Right. I should be. Am I still visible? Doesn't matter anyway. Clearance. Yes. Right. Let's crack on. It's very difficult. And some of you have done this. If you're presenting to nothing, it's not handy if you can't watch people's eyes and realise they're getting very bored and things. One of the things we always concentrate on making sure we obey the law and the European encouragements and ALARP and things like that. We forget we have to sell this stuff, at least quite often. We've got to sell this stuff to someone. And this is a link from the EMR website. It's one of the biggest scrap metal merchants. You'll notice the bit in bold with the red bit. And we are included amongst things like asbestos, PCBs, ammunition shells and other explosive ordnance. So that's what we have to satisfy these people, that if we sell them this stuff, it's not too radioactive. The usual disclaimer, just I mentioned a piece of kit, I'm not saying it's best for you. I'll go through it quickly. We had some, it was good enough. And it's the ability to be confident that the people using the measurements are comfortable with it, because you have to appreciate that the quality of any measurement comes down to the person actually doing the measurement on a regular basis. If you supply them with bits of kit they don't much like, then it will not be appreciated. So just because I mentioned a piece of kit, I'm not selling it. Obviously, there are huge numbers of manufacturers who want to sell you equipment like this, and I get a lot of heat from people. They say, "Why didn't you talk about ours?" And so this is my reason why I didn't talk about theirs. That's wonderful. So first IT glitch. Never mind. Right, try that. Okay. Let's try that again. Good. Right, clean. Clean is only by history. I will interrupt anyone in any forum that talks about clean and dirty. Americans are prone to this. This is rubbish. Clean is only by history. Things can be in scope or out of scope, or below the limits or above a limit, or some phrase like that. But clean's only by history, and that means no reasonable chance of contamination, no reasonable chance of activation. So if you wrap something up, take it into an active area, use it, monitor the wrapping, fine, there's nothing on it, remove the wrapping, that is clean. Something that's been in there, no matter how well you monitor it, cannot be clean, because somebody can always try a bit harder. And so that could be out of scope or excluded or some phrase like that. So not clean is only by history. Benefits of exclusion are fairly obvious. It's, first of all, it saves huge amounts of money. And it involves and probably the reason you're not paying someone to take the stuff, you're not paying to pack it up particularly well. You don't have to transport it long ways. So, and obviously LLWR is a finite resource. We should only put stuff in there that really deserves to be in there. And it's the same with any other waste facility. Some of the VLLW ones, we should only put stuff in there that deserves to be there. For a while, the process of clearance, the phrase was, "Oh, it's all too difficult. Oh no, we don't have time to do that. And we'll just hoof it into the active waste process," which was a terrible, terrible waste. There's lots of legislation and guidance. I'm not going to read it, obviously. EPR is mostly the environmental permitting regulations, are the one that really dominates when we're getting things off-site in its various forms. Behind that, this RSG 1.7, which is under revision at the moment, the top one, IEA Safety Guide, is possibly one of the most useful ones around. That's where a lot of the numbers come from. But under that, there's all these EU recommendations, which have been the scientific basis for dealing with this process. And all of these things are taken account by the Clearance Exemption Working Group, NICOP, Nuclear Industry Code of Practice, which is a very useful document, which we continue to develop with enthusiasm. It's weak, I will admit, on dealing with surface contamination. It's extremely good when dealing with bulk activity. Regulatory guidance is always very handy. It's nice to know how the regulators are thinking, because ultimately they're one of the people that you have to convince. So all these things are based on activity per unit mass. The unit is dimensionless. This is what it is. It's basically, it's the sum of quotients. You take the activity concentration in becks per gram, you divide it by number, you add it all up for all the nuclides that are present, and if it's more than one, it's in scope, and if it's less than one, it's out of scope. Shelley, my lady, invented the phrase the oozle, out of scope lever, out of scope limit. It's got a lot of advantages. It means whoever's working, your supervisor can come in one day and say, "Hey boss, we started this week, it was about 0.2, 0.3 oozles. Yesterday it was up to about 0.5, 0.6. Today, the first 2 or 3 things have been up at 0.8. It is going bad on us." So it's a useful shorthand. So if it's less than 1 oozle, it's out of scope, and if it's more than 1 oozle, it's radioactive under the legislation. RP89 and the CEWG, there's a surface activity level, becks per square centimetre divided by nuclide specific becks per square centimetre. This doesn't have a name yet. We'll have to think of a good name for that, because we haven't taken surface activity seriously, perhaps, as bulk activity up to now. The averaging areas and volumes are not specified in regulation, which is really interesting. We had a very near miss a long time ago. On the way back from work, Shelley was telling me all about the debate about averaging areas, and she said, well, the setting on, this is one of the Article 31 group, was it? Setting on 300 square centimeters. And I went, what? That's ridiculous. Go ask why. And she asked, and it went up through the great and the good and came back again, and it came back with the phrase, we don't know. What would you suggest? So I said, we go for a square meter. We won't get it. But essentially, if you're talking about relatively homogeneous stuff, you can get away with averaging masses of a ton and averaging areas of 1 square meter. This is very different from routine health physics operations. This big averaging area is the problem that you will have to sell to the people doing the measurements if they're health physics people. You're aiming big projects, close to a ton or square meter, you can justify based on homogeneity. This gets a bit vague, but hotspots make life much more complicated. Why is it useful? The bigger the volume of the area, the fewer the number of measurements you have to make for a building or a floor or anything like that. The higher the signal is available to, the more activity is available to you in the sample, and the larger the detectors you can use on that job. So the high volume of area and large detector, the quicker you can get to required statistical uncertainty. So it makes huge benefits. Using large areas and large volumes makes for robust and, above all, quick monitoring. There are constraints, obviously, but if you can do that, it's worth it. What's a hotspot? Magnot's terminology is an area of elevated activity. Yeah, fine, okay. Well, I think in our world there are two kinds of hotspots. The dosimetrically difficult one that you have to worry about in terms of giving people doses in millisieverts, tens of millisieverts, hundreds of millisieverts region. If it's inhaled or swallowed or gets lodged under a fingernail or something like that. And that tends to be tiny bits of irradiated fuel. Make sure these are impossible. Starting to do in clearance with any reasonable possibilities around is a bad idea. The other kind is much larger, dosimetrically less important. We find lots of cases where a pipe from a sink going through a wall has cracked, and you get a halo of contamination around the crack. In some ways it's a hot spot, but it's dosimetrically unimportant, and it's also very easy to remove, but you could average it without actually being radiologically, what's the word for it? Radiologic, what is the word? Never mind. Irresponsible, that's it. This is always the argument with waste, a lot, as low as reasonably achievable. If it doesn't cost that much to remove activity, just do it. There's endless numbers of clever and much debated ways of working out the cost-benefit relationship, most of which do my head in. And we've got two aims. One is to reduce the potential of those, but the other one is also reasonable, is to lower the waste category. You get into an interesting argument where you say we don't have any ILW at the moment, but if we take all the hotspots out and put them in a drum, that then constitutes ILW. So you've made us have an ILW volume from this project. My feeling is if you can do that, then yes, tough, you've got an ILW volume. The ONR have their own take on this, and it fulfills the same requirement. We have to think about ways of removing activity from a waste stream if it's a LARP or a LARA. Now we got a lot of heat about this thing being very nuclear biased, and quite long, about 11 years ago, we started a project to produce SRP advice. My one criticism of SRP is they have been extraordinarily successful at hiding this document in slightly weird places, like you don't find it under documents, for example, you find it under advice. It's very in need of revision on legislation, etc. Now you won't be able to see that, but the picture of the red brick Edwardian building below has the radium wing written on it. And it was, so they had the working title of the horrible moment when you realise why the radium wing was called the radium wing. Up till then it had just been a name, but then you realise it came with baggage, lots of baggage. Nice Professor Marsden worked a lot on this, and he has a nasty, dangerous sense of humour, particularly in print. Is this all real in this SRP thing? Only the names have been changed to protect the innocent. You have to be very old to understand the reference. I don't know if anyone will, but we did generate the site from hell. It's a merry compendium of all real examples under one convenience site. And we also dealt with less problematic things like treating contaminated fridge. I think this is a super document. It has not had the airtime it should have done. It is not as people are not as aware of it as they should be, and I commend it to you utterly, particularly if you're not, in the words of Peter Marsden, one of those nuclear Johnnies. Because this was written specifically to deal with people who are not nuclear Johnnies. Measurements time. Well, you think of it, quick splits, industrial sites, small range of nuclides, luminizing thorium, norm, hospitals and universities, nuclear generating sites, fission products, fuel leach, activation. The interesting ones about that is that nuclear generating sites start off with usually quite simple fingerprints. We have the fission products, which when it gets old and tired is dominated by cesium-137 and strontium-90. And we have fuel, and what can happen, particularly in drains, this is something always to watch about, particularly if you're a physicist. Speak to a chemist, think about chemistry. I learned an awful lot about that working at MPL. Because there's all sorts of physical and chemical processes that influence what gets out into, for example, drains. And it can go in one very familiar angle, go from basically hard betas with lots of gamma to virtually all alpha. So you have to be really careful with the fingerprint and that you assign, and really careful on checking the fingerprint as you go along. And then we're back to the nuclear research sites, most of which have been done, mostly. And the argument is if it has existed, it might be there. This is the curse of Harwell. If it's got a reasonable half-life, it might be there. And then, again, something very much less familiar, accelerators. You get some very unfamiliar to most RPAs and most instrument techies like me, some very unfamiliar radionuclides formed as activation products in accelerators, which will challenge you. The other problem with a lot of these things is if you look at these various documents that give you advice and give you clearance levels, they give quite a big list of clearance levels, out of scope levels, what a reference level of some sort. But what they tend to do is have a very conservative fallback position. And one of the classic ones is, if it isn't on the list, it's 0.01 becquerels per gram. Now that can be an extreme curse because lots of these radionuclides are, by any radiological standard, not important. They are low significance nuclides, but it could drive you into putting these things in a very high waste category. So you have then a problem of dealing with these things. You can do it properly, which means running it, getting someone who understands all the models used to derive the various reference levels for the various radionuclides and getting them to run these particular nuclides. We did that for calcium-41, which is very, very popular in concrete, wasn't in any of the reference levels at the time, and it's a miserable electron capture nuclide. It's a radiologically of extremely low significance, but it can be the dominant activity. And so we had that one assessed properly. My inclination is if you have one that doesn't appear to be, that it appears to be a low toxicity one, I would try making the case that you're going to adopt one of the values from existing radionuclides based on a compare and contrast job with what your new nuclide emits. That is a decision between you very much and your regulator. It particularly pops up with accelerators. Right, waste characterization often refers to a fingerprint or a nuclide vector rather than quantifying individual nuclides. And this is the thing, there'll never be a becquerel meter or a Nusselt meter. And people will say, well, fingerprints are too much hard work. This is wrong. You cannot do anything to a material unless you understand the performance of the instrumentation you're going to take to it. Any detection mechanism is radiation type and energy dependent. What's the right instrument? One that gives you lots of counts per second per ousel, preferably above a fairly low background, and one that isn't violently dependent on fingerprint stability. If you can find one, you're lucky. We have fairly well avoided worrying perhaps as much as we should about fingerprint stability. It's something you do need to think about because it will change as time goes on. We don't have time in this seminar to deal with it, but there are lots of ways of confirming that the fingerprint isn't moving that fast or to a very large degree. Becquerels are only a step on the route. They're always only a step on the route. And I get fed up with people getting worked up about becquerels. They have no automatic significance in themselves. Anything radiation protection, they're always dividing it by a number. So you convert the becquerel fingerprint to an ousel fingerprint. Why not? Or any other nuclear-specific endpoint. You can do it for that. That makes sense. And it shows you, if you do that, what is really important. Something that might only be 1 or 2% of the fingerprint in terms of activity concentration can end up being the dominant one in terms of ousels or radiologically. Really important, alphas win out all the time, energetic gammas, and heads of chains in particular. And what generally is less important, short half-life, low energy betas, electron capture nuclides, etc. So always turn your fingerprint into an ousel fingerprint to get the significance of it. Won't go through the list, but we've got cobalt-60, higher toxicity, lots of energetic gammas, relatively short half-life, but a huge amount of energy, 2.5 MeV as gamma radiation. It has a low limit and it's inactivated steel. You can see why cobalt-60 is so important, because the world is made from steel. Do you want to have breakfast next to a fridge which is at least partially cobalt-60? Most people aren't comfortable with that idea, and reasonably so. So when you run it through the various models, you realize that it is dosimetrically significant. And of course, we've got our friendly Plooch 239 at 0.1 becquerels per gram. So, and some other ones. Iron 55. Iron 55 is a very dull radionuclide. If you've got activation in steel, you get lots and lots of iron 55. Many of you will not be familiar with iron 55. It's a 36% emitter of a low energy X-ray with a fairly short half-life. As such, it has a deservedly fairly high out of scope limit. Nickel 63 is the same. It's got a very long, much longer half-life, but it's a very low energy beta. And we go through the list. Right, you want to do some monitoring. Start with your ambition. What do you want to say to people? It's nice sometimes, politically, financially, to say that the material you are offering someone or intending to remove is indistinguishable from background. It's a dangerous phrase. It's very easy to be indistinguishable from background. It means if you don't look properly, it will be indistinguishable from background. Or do you want to convince, produce, be able to be confident if it's in or out of scope? Or do you need activity for waste declaration? The thing to do about this, remember this, if you want to take something apart, if you want to clear a building, and you think it's indistinguishable background, it may in fact be clean, but you cannot demonstrate that it's clean. Measuring bits of junk which all turn out indistinguishable from background is dull. I had the pleasure of doing a seminar on this at Culham. There was about 100 people there, and in the middle of a bunch of guys in coveralls. And I got to this bit, and I said, well, how might one describe clearance measurement? And I looked at this guy, and you could see he had a view, and he went, dull. And he came across and apologized to me afterwards. Said, no, that was brilliant. The best actor in the world couldn't have done that better. He said one word. Everyone in the room realized how mind-bogglingly dull. Monitoring lots of things, all of which proved to be compliant. It's utterly boring. Even the best comrade will be tempted to cheat. And it is a waste of the skills of a good radiation protection technician. They shouldn't be sitting there doing an integrated measurement with a beta probe for 60 seconds on lots of tables. and they spent 2 weeks doing this. It is unbelievably boring. Machines are better for that. The other option is it may be better to train people specifically for this job, because there are people who are very comfortable in jobs like that. They will do them extremely well. They have a different view of what they want from life. And it might be better actually to train people specifically for this, because if you start using good health physics technicians, surveyors, monitors, whatever you want to call them, to do clearance monitoring, you have to untrain them in some ways, and they will, the good ones, will find it extraordinarily dull, and they will tend to cheat. Right, let's see one aim that just materials indistinguished from background. Everyone's seen monitoring. We've got the probe and the rate meter and the tick-to-tick bit, and the guy carefully waving it over something like that and looking up going, yeah, that's okay. That is extraordinarily difficult to quantify. It's impossible to audit. And when you look at the levels we try to get down to for clearance, and honestly, the sensitivity is probably marginal. So rate meter based clearance measurements are often not a good idea. Your better option is integrated counts. Now, there is nothing stopping you setting a short time. You can set a 10-second integration, which is the sort of time that as you scan over a surface with a rate meter, as you spend waiting for the indications to stabilize. There's no need for user judgment at this point. You get a digital answer, and it's very, very easy to audit. If you're in a position of responsibility and your people give you numbers for this thing, you can plot them, and you can look at the resulting frequency distribution for particularly integrated counts or average count rates or whatever. And it means you can say things, you have a curious count distribution, Mr. Ack said, I think we need to discuss this now with the door shut. So, i.e., you suspect Mr. Atkinson has been making it up, and that shows up really, really easily if you do integrated counts. And it is this concept of auditable. If somebody comes along and says, how do you know all these people are doing it right? You can go up to someone and say, Miss Johnson, and she turns around and says, yes, Gav, can I, you got a number for that piece you've just done? Yeah. Can I use your, look, there. She got 10.6 counts per second in average. I've got 10.4 or 10.9. It is the same answer. You can redo it. It's also easy to calculate a point of suspicion. The point where you look at it and go, I don't think this is background, or I think this is contaminated. And it's easy to calculate the maximum miscible activity, i.e. the activity that you stand a small chance, only a small chance of failing to identify as above whatever limit you've got. How to employ this? Balls with low level expected to be acceptable surface down. Gradient meter squares, press the start button, scan the probe evenly over the current square, aiming to get to the end of the square at the time. It's surprisingly easy with practice. You can get right to within 2-3 seconds, something like that, quite consistently. Record the number, sense accordingly. It's very, very different from routine RP surveying. You get the question, what if it's on the one spot? It's back to the ALARP argument. You're still listening if you get a high count rate. Stop and find the maximum. If it's unacceptable, deal with it. If it's acceptable, then restart. But one of the arguments is if you find a hotspot and you've got no concept of expecting hotspots, then that is a real red flag. You've got to think about that really hard. If you're being ambitious and the limiting count rate isn't that far above background, it might just be statistics. The gods have a wicked sense of humour. They usually wait till you get to about the 56 second, they go at you suddenly. Just restart. And this was a nice line from one of the very competent HP health physics technician. He looked at me one day and said, my head agrees with you, but my heart is against it. I pointed to my invisible extra stripe on my shoulder and said, on this occasion, I am giving you an order. I respect your view, but you will do it this way. And about 2 weeks later, or a few days later, he phoned up and said, you're right, Pete, I've got my head around it now. It all makes sense. Because when you spent 20 years of your life identifying, scanning very carefully over the surface and finding anything which is of significant activity, then averaging over a large area is difficult. It's not something you find easy to do. I keep getting clearance certificates with this rubbish written on the top. 0.4 alpha and 4 beta becquerels per square centimetre. It's from the dark ages. This has no business to be in any sort of clearance process whatsoever. I get really angry with people because I phone them up and saying, you have a DP6, and they go, yeah. And the response to becquerel per square centimetre is about your fingerprint be around 17 counts per second. Yeah, thereabouts, yeah, I'll go for that. So 4 becquerels per square centimetre be around, chucking in background as well, I'll call it 70. Yeah, that seems pretty fair. Would you really send me something with 70 on it? Oh, no, definitely not. I said, well, don't issue clearance certificates on, because it's stupid. It makes people who are not familiar with the nuclear tendency to be cautious, gives them the impression we do let stuff with this level float around, which we don't. So this is from the dark ages. Get rid of it. It made sense in the 1950s. It made sense to John Dunster, but we're 70 years later. Active or not, everyone should have a copy of Curry. I think it's amusing. We've got Curie and Curry. If you read this paper, the opening paragraph is very clearly written after seeing his umpteenth dodgy definition of detectable. You can almost sense the frustration of reviewing a paper going, oh, not another one. And so I got the impression that Lloyd Curry sat down one Sunday afternoon with a big pot of coffee and thought, I'm going to beat this to death quantitatively. And he produced this paper. Now, people snipe and carp this paper, but it is still, I think, very relevant, and it is very clearly written, which makes it unusual for or very understandable, which makes it unusual for a statistical analysis. And it's a super paper. I commend it to everyone. There are no free copies on the internet. The point of suspicion. It's numerically same. Curry calls it a critical limit, which I don't find a very convenient phrase. It's easier language. It's the point where you go, I don't think this is background. At which point, maybe you're comfortable with that, but it might prompt an action to remeasure an average, for example. If you were making the case that the material you were shipping out of this place was indistinguishable from background, that's the point where you think it is distinguishable from background. So you have to do something. It's just people put this number in. You say, what are you going to do about it? And they go, look at you and go, what? I said, it has to prompt an action, one of these things. If you set it at the mean count rate plus 2 sigma, mean count plus 2 sigma, one measurement in 40 will be exceeded just because of statistical variability. You can set that. It's a very useful concept. Curry's got a thing called the limit of detection. And we're all fairly familiar with that. Said the limit of detection for this measurement is, now it doesn't actually mean that when you look at it. So somebody threw away the word something like statistically likely, because the limit, if you work out the limit of detection according to Curry and it turns out to be 20 kilobecquerels, then you will frequently find 10 kilobecquerel sources. And I think that's looking from above the value downwards. When we're clearing waste, we are trying to decide that we are not above some limit. So we don't have a limit of detection, we have a maximum miscible activity. And it's very approximate to something, it's background plus 4 sigma on average. So if you had a background, you were doing this table, what have you, and you expect 100 counts within your monitoring period on average, then sigma on that should be the square root of 100, which is 10. So you can say that you have a point of suspicion of 120, because that will turn out one time in 40, and that will prompt you to remeasure, for example. But something that almost always gives 120 will have an average activity corresponding to 140 counts per second, 140 counts. So it's not difficult to calculate, and enables you to be very cool and sit in front of in meetings with people saying, you ask them the background, they go, well, that's going to give you maximum miscible activity is going to correspond to whatever gives you 10 counts per second. And they look at you and go, wow, that's so cool. We did it properly and it came out at 11.2 or 9.8 or something like that. You have to set statistical significance on this, because you may be doing thousands of these things, in which case you don't want to stop for 1 in 40. On the other hand, you may be doing only 20 or 30, in which case stopping and remeasuring 1 in 40 is no big deal. You set statistical significance. That has to be very clearly expressed as well. So, how do you work out the point of suspicion? Identify fingerprint. Choose an instrument or detector. Work out the response to the fingerprint. Still looks a sensible instrument. And if you want to make the case that it's indistinguishable from background, you find a clean reference sample for each object category, because every time you put a different thing in front of your beta probe, for example, the background will change, because the thing will give you different levels of gamma shielding, etc. It will have its own natural activity, which you're prepared to accept. If you're dealing with tiles, for example, they're obviously active. You identify a low background area to work in, perform a long count, and then that becomes the reference for that sort of object in the next 2 hours. You then sit down, and if you're managing it properly, you sit down and do 500 or 600 of these objects, or however long it takes you to get through the back. You go through this process anyway, I won't go through it, but you work out what is the maximum miscible activity. Now you have to ask yourself the question, is it good enough? We can work out, and if you work it out, and it's good numbers tend to be about 0.1 or 0.2 oozles, probably about right. We say the maximum activity is about 0.2 of our out of scope limit. Less than 0.1 oozles, you're trying too hard. Cut the integration time. Saves a lot of time. If it's a bit high up, 0.8 or 0.9 oozles, is the measurement really good enough? Consider increasing the counting time as an easy fix for that, but remember the improvement is the square root of the factor of increase in time. So going from 10 seconds to 100 seconds will give you a factor of 3 reduction in the maximum miscible activity, something like that. But if you want another factor of 3, you've got to go to 1,000 seconds, and that's becoming totally impractical. If you do the calculations for the instrument you think will work, and you find it's out of scope, and the time you'd like to spend on this, if you get more than 2 or 3 oozles, then you probably have the wrong instrument, because messing around with the time will not help you fix something like that. But you have to accept that it might be impossible using direct measurement. There are fingerprints, there are lots of fingerprints where you cannot do it by pointing a radiation detector at the object of interest. The classic one recently was doing the Amersham Cardiff site, where the delicensing process was driven entirely by samples. Far more expensive, far slower, needs more planning, etc. But with carbon-14 tritium, that's as good as it's going to get. One of the interesting things is how twitchy is the result. Look at the fingerprint variation. Move the percentages of the radionuclides around. The bigger the count rate change per oozle, the more you need to worry about fingerprint instability. Classic one of that is where you're using gammas to control, to deal with a fingerprint which out scope level is dominated mostly by alphas. So you might be using cesium-137, but what you're really worrying about is Plut-239. So obviously you're in a position where, and the cesium-137 might only be a few % of the activity in terms of oozles. And so a small change in the cesium to Plut-239 ratio will give you a huge change in what constitutes an oozle for that fingerprint. So it needs to be assessed, it needs to be assessed carefully. But again, you may be in a corner where that's as good as it's going to get. You can deal with lots of these things in the monitoring process. If you get a common problem with a fingerprint with a mixture of hard and soft betas. Soft betas, close approach, and a good surface. Not something dusty. So check. What happens if we deliberately ignore the soft betas? Do we still have a decent response? Good, fine, that sounds good. So add an absorber over the window and maybe move back again. That means you don't see the hard soft betas, you still see the hard betas. It gives you a bigger averaging area and less worries about surface condition. It can be greatly advantageous to deliberately ignore some of the signal. We did this in a stack contaminated with protactinium-231. Nasty asbestos reinforced cement material. And we went through the whole process. It had basically ingrown because it was about 60 years old. So what did we have to do the monitoring with? Lots of alpha decays. So you've got a dusty piece of concrete inside a stack. You're not going to use that. You can't do alphas on that. There's a low energy beta, too low to be useful, but two nice, big, grunty, energetic betas. Lead 211, thallium 207. So we took thermo BP19, Ludlam, thin window beta probes, both respond efficiently to energetic beta emitters, and we just stuck a piece of 8 milligram per square centimetre plastic sheet over the end, and we recalibrated it using chlorine 36 and strontium 90 with the plastic sheet in place. The measured response to the fingerprint was 80% of the open window values, because again the BP19 and the Ludlam weren't that good at seeing the alphas. So at the end of the day, we had something where we had a much more stable, less condition dependent response, and the job went like a dream. Another example, Winfrith East building, 300 cubic meters from the SGHWR, correctly the steam generating heavy water reactor. Britain's take on the can-do. Yeah, very high maintenance, very high operator doses. If you read the Wikipedia entry for it, it's very complimentary, but certainly as far as radiation protection people are concerned, the SGHWR was a bit of a beast. So with this building, we're going to treat the sludge in. It's a relatively new building, big start, because the newer the building, the better the history. Everything happened inside a cell line. Only a very small number of incidents actually happened inside the cell line. So we decided to make the case that the rest of the building was clean. We took the cell line out carefully, and the rest of the building was clean. We had some interesting things to remove, like we realized that some of the equipment had been brought in. We found it a mildly contaminated lathe, for example. Mixture of activation products, fuel leakage. The nice thing about it, note the 0.06% alphas. So go through the list. The easy one, cesium-137, easy to detect as a beta. Nice, medium energy beta. TP6, why not? And so we worked out that the corresponding fingerprint activity, the maximum miscible activity was 0.15 becquerels per square centimetre for a surface. And for all barring very thin material, like sheets of plastic, bits of paper, that would meet the then current, then solar substantive low activity exemption limit. So it was fine. Reworking it under EPR, again, demonstrates that basically the limiting cesium activity in this case was 0.19 becquerels per gram. And so we could actually reliably make measurements for that fingerprint with that instrument quite happily under EPR, and make some nice robust statements for anything more than about 1 gram per square centimetre thick. As homogenized rubble, for example, it was clearly out of scope. Then we get the measurement by wipe thing. We've talked about instrumentation. Smooth, complicated stuff, success removal activity. 10% pickup factor assumed. Probably conservative in this case. Lots of reviews of this. Lawrence Warren did a rather nice MSc in this, and the values mostly in the 10 to 30% range. And so we found we could use wipes on difficult, complicated shaped surfaces quite effectively. Again, something outside the nuclear world, radium. We keep finding radium. This usual argument, it's all RAF sites can be treated with suspicion. Anything the word RAF maintenance unit on it has very big levels of suspicion. The nice thing about it is that if you look at the aircraft instrument on the left, they were built to superb quality. Probably nothing has gone out. So if you see one like that, it's all inside the dart. The one on the right, however, is bad news. It could be all over the place. See the decay scheme, freely available on Wikipedia and many other publications. Problem with radium is it decays to radon 222, which has got a 3.825 day half-life, and well, it can escape all the useful betas and gammas are after it. So your presumption when you're doing any monitoring for radium is that there has been some degree of radon retention. So how can you check? Nice thing, a friend of mine did this. So he filled the drum up with radium contaminated chalk and put the lid on it most firmly, and then came out every morning for 2 weeks and measured the dose rate on the surface and gently watched it climb as the radon, which had escaped during the excavation process, gradually re-established itself. So you go off to your friendly aviation museum or whatever, and you got all these Lancaster bomber instruments and things. Well, you take the instrument out of the box and you check the box. See if there's any count rate at all. If there is, you come back 2 hours later. If there's not even much in the first measurement, the radon hasn't escaped. High build quality, low radon escape. So the paint hasn't escaped, so that one's fine. That instrument is contained, it has an activity, but it's not a leaky source. If you get significant initial count rate followed by it all gone pretty well, then it's radon. Radon will get out of certain things and not a lot of loose contamination. If it's still there, you have paint fragments, and your life has suddenly got a lot more complicated. And it's very easy to assess the activity. There's one for Mini 900D, which is an instrument I deeply love using for this sort of thing. You can work out for your own instrument. So this is the thing, if radium's an alpha emitter, if it's in paint on normal scale, alphas are not monitorable. But if you're dealing with norm, residue from oil exploration or paint manufacture like, once it's more than a few weeks ago, all the bismuth 214 and lead 214 will have grown in. If you get really old radium, then you get an extra beta from the lead 210. That doesn't apply mostly to scale where there's a process to deliberately extract the radium. Right, you got significant gamma, cobalt cesium-137, for example, or bismuth 214 radium, or cobalt 60, less likely, but typically quite often cesium-137. And you want to monitor in bulk. Reasonably homogeneous, again, we've touched on this, but it's worth going through this again. A dial or a fuel particle or something destroys the reasonably homogeneous idea straight away. If you go to, say, the 20 kilogram level and you can visualize your 1-ton bags swapped out into 50 pieces or something like that, and you can find no more than 5, well, you won't find one of those with more than 5 times activity concentration. That's an argument to make for homogeneity. Nobody expects it to be perfectly homogeneous. Okay, a few useful instruments. Handheld inorganic scintillator gamma spectrometers. RIDS, however you want to call them. But not to find out what's there. History defines what's there, and analysis of the at the beginning of the project confirms what is there. Be very clear about this. If you find something in your analysis which isn't in your history, you don't just add it in. You have to go back and you explain why it's in the history. So the history should be a real robust account of why this piece of material either contains or potentially contains this mix of radionuclides. But these are very good for checking nothing unexpected has turned up. I got phoned up one day by a guy called Mick. He said, Pete, he said, this job we're doing, do you want to come down and look at my GR130 handheld gamma spectrometer? I went down there and looked, said, you got americium in that, Mick? He went, you think so too? I said, oh yes. He said, americium-241. He said, interesting, because the fingerprint doesn't have any in it. And this had been a volume of ground which had been sampled to bits, and nobody had found the americium, and we ended up taking a lot of americium out of that contaminated waste, out of that hole. And that was based by using a simple handheld gamma spectrometer. You can use it to compensate for variations of legitimate naturals. Different kinds of brick, different kinds of tile, different kinds of made ground will all have different natural content, and you can use it to use this device to compensate for that. What do you count? You get a great big spectrum out of this thing. Source on the surface, use a photopeak. Distribute activity and maybe a wider window. And the usual argument is if you're dealing with a big thing, then the bigger the better. Do not be mean about buying these things. You'll find that time is hugely expensive. Buy the biggest one, which you radiologically can take the job, and which is actually manageable. That's often the limitation. Yes, Gov, it's fine. It works really well, but I refuse to try lifting this for more than a half an hour a day. It can be a position you're in. Long time ago and far, far away. There you go. There's a quote. Exploding GR130 changed the rules. See a picture of it here. On the right, the very simple liquid crystal display. There are newer types. There are lots of newer types. The advantage is the better displays. It's a 20-year-old display. It's a 20-year-old instrument. Bigger detectors, different scintillators, which have different energy resolutions than that, and temperature compensation. So handheld gamma spectrometers are enormously useful if you're dealing with bulk waste in any sense. Beta detectors again, lots of these again. 100 square centimeters seems to be a handy size. Big enough to be sensitive enough and cover the area of interest, but and manageable. Bigger is useful for distributed source and good access, but they become much more clumsy. Now, we're all used to considering spectra from gamma radiation, but you can do energy counting windows on betas. Again, this is not a subject for this seminar, but you can do lots of useful things where you can compensate for naturals. You can identify the quality of the source, for example. You can check on this fingerprint stability, like why has the beta to gamma ratio suddenly gone screaming up? Do we have some extra strontium-90 we weren't expecting? And it improves the maximum miscible activity. So you can be quite creative with using quite common beta detectors and instruments such as the old Electra now and its successors and parallels, which have energy selective windows to actually improve the metrological process. And there you go. I galloped through this, but this is the thing, really important. Good monitoring saves money. I got fed up sitting in front of project engineers and explaining to them that, oh, but this is all terribly expensive. And then saying yes, but it'll save you lots of money. And on one occasion, the comrade and I were roundly hassled for saving 20 half-height ISOs. I had no idea how many millions that cost. And the fault in that project was that the monitoring costs sat with the project, but the waste costs sat with the site. And this is an extraordinarily bad idea. The waste costs and the monitoring costs has to sit with the project. Otherwise, wrong and poor decisions will be taken. Anyway, thank you for your attention. It's